So today we will talk about quantum mechanics. As simplest quantum field theory. It will be point number one. Point number two would be why QFT is not as constructive as quantum mechanics. Point number three. Observables in quantum field theory. So probably I'll put it here. Point number four. In quantum field theory and I would say versus Feynman approach. And it will be quantum field theory with Planck constant. So which is the plan for today? Reminder. Quantum mechanics is a symmetric monoidal functor from metrically enriched one cobordisms. Full tensor algebra. In simple terms, we have an interval of the length t. To this integral of the length t, we associate f of T, this belongs to endomorphisms of L times functions on R plus. So point correspond to the state L. Now functional reality. More it takes morphisms to morphisms and composition to composition. In cobordisms, T1, T2. In tensor algebra, F of T1 composition with F of T2. I'll write it like this. Comp means composition. So here is the functor. And here is the functor. So this diagram is commutative. Maxim, is the board clear?
Yes.
And this has a nice solution. Moreover, this is classification theory. All cobordisms, all smooth cobordisms are like that. Remark. Remark is physics, but non-relativistic physics. Relativistic. Example. Consider a particle. Let us say electron. In magnetic field. In magnetic field. Its L is c square, called spin. Its H is a mu sigma mu. Mu going from 1 to 3. Okay, AI. Sigma I. Sorry, not even AI. It's called BI. BI are components of magnetic field.
And the camera lost focus.
1 second. Thank you very much. So is focus back? Is focus back?
No.
No? I'll correct it. 1 second. It should be back now.
Yes, all right.
Main object e to the e h. Actually I. So people use I in physics. So it's okay. Let me put here I here. I'm sorry for changing notations. Unitary rotation. Of spin. So it is the simplest quantum mechanics available. Example 2. Two electrons. Now L is more complicated. L would be L1 times L2. What L1 is? Functions on R3 is our space times C square. It is a spin. L2 is also functions on R3 times C square. You may ask, what is Hamiltonian? Okay. So Hamiltonian is U is E square, and here I have R1 minus R2 R1 its coordinate in R3. Coordinate of first electron. R2 is a coordinate of second electron. So I have this. So H, let me call it H electric. It maps from functions R3 times functions R3 to the same space. So HE may be considered as an operator from L1 times L2 to L1 times L2. Now there is also HM, and HM is, so here E, I would even write, yes, E, is the charge of electron. And here is also HM, that is sigma A first, sigma A second, and here I have sum over A, and here is some magnetic function that I don't want to write. And this is spin-spin.
Sorry, can you repeat what is sigma?
Ah, it's my mistake. It's my mistake. Sigma A are operators. C square to C square called Pauli matrices. So actually, for mathematicians, they are SU2 generated. You see, I'm sorry for not mentioning it explicitly. Physicists
Okay.
get,
Thanks.
you see that this I is square root of -1. Okay? And similarly, when physicists are writing sigma, for them it is as standard as writing I.
And what is B of A? Sum of A,
Sorry,
B.
BI are components of magnetic field.
Oh, thanks.
This thing in physics is called interaction of the spin degree of freedom with magnetic field. However, I'm treating it as a mathematical object. You should not try to think about it otherwise than mathematical definition. It's an example. This example shows how formal structures that I'm explaining to you are related to real world. In the real world, you have this. And in the real world, if you have two electrons, there are positions of these two electrons, but they also have this mysterious spin. So that's why the space of one electron is L1, and there is a space of the second electron, it's called L2. And there are two operators. and H, and here I also put E square, and E is a charge of electron. So then I put H, that is HA plus HM.
Sorry, it's a little bit unclear. It's a sum over just to sigma.
Okay, so when I have a, thank you very much. Once again, here I have tensor product. Sigma A1 acts in C square 1 of the first particle. Sigma A2 acts in C square 2 of the second particle. So each L1 have its own C square. When I take tensor product, okay, since it's an example, it should be given in detail. L1 times tensor L2 is a function on R3 tensor R3 tensor C square that I call first, tensor C square that I call second. Now, operator HE X here, tensor 1, tensor 1. So I wrote it, I'm sorry. I will rewrite it again. HE is E square R1 minus R2 square. HE applied to psi R1, R2. So psi, okay. Psi R1, R2 belongs to functions on R3 times R3. It is called psi function. Element of L is a psi vector R1 or 2 that belongs to tensor C square 1 This is the explanation of the vector that I put here. Physicists write it as psi alpha 1, alpha 2, R1, R2. These is called are called spinor indices. To explain the relation between this and this, I just say that let E alpha 1 be a basis. Sorry. Okay, it's okay. In C square 1. Similarly, E alpha 2 be a basis in C square 2. Then general element of L is psi R1, R2. That is E alpha 1, 1 tensor E alpha 2, 2 times psi alpha 1, alpha 2 R1, R2. So physicists call this spinorial degrees of freedom. Called. And these people called space degree of freedom. So what about my camera? Is it okay? Maxim?
Yes, all right.
Okay, so when we are writing things like this, it's real physics. So in my course, you will get combination of mathematics and physics. That's why it's called mathematical physics. So I will pick up examples from real physics. And now, HA acting on psi R1, R2 equals to psi R1, R2. H magnetic acting on psi R1, R2 is E squared. And here I have this operator. something like this. So what do I mean here? This term is so-called function that describes that spin of the first particle creates a magnetic field outside it. And that's why it's acting on the spin of the second particle. Okay, so these are words in terms of physics. In terms of mathematics, this operator is acting on the spinorial degrees of freedom. This function is acts on radial degrees of freedom. Altogether, HM is a tensor product of two structures. So this was to show you how quantum mechanics happens in our real world. And then we may study evolution of the system of two electrons. And evolution is given by the operator e to the th, evolution. So let me tell you what can happen in the process of evolution. I forgot something. I forgot something. I'm sorry. And there is a term that I forgot that is H3. And H3 is d over dr1 square plus d over dr2 square. So now I completed the example. So this corresponds to free motion of electrons. This corresponds to electric exchange, and this corresponds to magnetic exchange. So first, U2 H3 electrons would move second. U2 HE their rate. Motion would change a bit. They would repel. So in classics, we would, in classical world, we would expect something like this. However, in quantum mechanics, picture is different. Different. Psi 3 is e to the I P1 R1 tensor e to the I P2 R2. Now H3 take psi 3 and takes it to e to the t P1 square over 2 plus IP2 square over 2. I put IT. So it is a change of the phase. So here P1 and P2 are parameters called momenta. So it is simple. However, we need to study HT, HIT. So here we have H3 plus HE. So it is complicated. But we will do perturbations theory. In E square. So it is approximately e to the ITH3. And here we put 1 plus ITHE plus O of E square. So what does this thing do? This thing says that H3 is going to, psi 3 is going to IT by 1 square over 2 by 2 square over 2 psi 3 plus IT And here I put this E squared, R1 minus R2 squared, psi 3, okay, plus O of E squared. So what does it mean? It means that the state corresponding to free electrons is the state corresponding to free electrons plus something else. Let me consider another state, free tilde. It is e to the IP tilde 1 R1 plus IP2 tilde R2. So this would correspond to two particles with momenta P1 tilde P2 tilde. So I can say that my H that was, well, let me call this object tire T. Is psi 3, okay, P1, P2, plus I would decompose this object in terms of this basis, plus T psi P1 tilde, P2 tilde, and here I have some object A that depends on P1, P2, P1 tilde, P2 tilde. So this A is called scattering amplitude. And we say that in pictures P1, P2 becomes P1, P2 plus integral over the space of P1 tilde, P2 tilde with coefficients like this. So particles coming together become linear combinations of particles going in the other directions with some coefficient. And it is clear how to compute it. This A is, roughly speaking, E squared R1 minus R2 square exponential P1 R1 plus P2 R2. And here is exponential it's exponential of I P1 tilde R1 plus P2 tilde R2. And here I integrate D3 R1, D3 R2. So it's an integral. You may take it as some special function. So quantum repulsion is this. And probably you have known the picture that people drew here. People were drawing things like this. P1, P2, P1 tilde, P2 tilde. And this wavy line corresponds to and it's called Feynman diagram. So it's an example from the real physics. You see, interestingly enough, I started with cobordisms, and I am coming to Feynman diagram. Now it's time for questions, and we will make a 10 minutes break.
I have a question.
Yes?
I'm sorry for the noise. There's something going on with my neighbors. I was wondering if the Hamiltonian is time dependent and even do not commute at different times. Can you still?
Hamiltonian is time independent here. In this case, Hamiltonian is time independent. And I need to say again that Hamiltonian, it was written here. But I can write it again and again. Hamiltonian explicitly is d over dr1 squared plus d over dr2 squared. So this is called free Hamiltonian. It's called free Hamiltonian. 。 . 。 。 。 。 。 . 。 . 。 . 。 . 。 . 。 . 。 。 。 . 。 . 。 。 。 。 . 。 。 . 。 。 . 。 。 . 。 . 。 . 。
Um, 。 .
。
I was wondering if the Hamiltonian is time dependent and even do not commute at different times. Can you still?
It's called free Hamiltonian. And then there was also interesting thing. E squared R1 minus R2 modulo A squared. And this is Hamiltonian of electric interaction. So both parts of Hamiltonian, this one and that one, so actually here the sign is minus, and actually here is also sign is minus. They are both time independent. So have I answered your question?
Yes. So, well, what if you have a system that has time dependent Hamiltonian? Can you is that still I mean can it still be described by the monoidal function?
It could, yes, it could be described not by monoidal factor. It's a good question, because in this case we need to go to another category, okay? So at the moment we discussed cobordisms in vacuum. The vacuum. Like we had this interval in vacuum without anything else. However, we can discuss cobordisms in a background. So let me try to explain to you what cobordism in the background is. Suppose you have some manifold Y. So now objects would be submanifolds. Say points of Y. Morphisms would be paths in Y. Y1, Y2, Y3, Y4. Okay? Now, composition. So it makes no sense to compose this morphism with this morphism, because these objects are different. However, it makes sense to compose it this way. So what you would have here would be the path groupoid. And the main thing would be the following. To each point I, alpha, you associate a space L alpha. Okay? So this is a point. This is a vector space. Altogether, you have vector band. To each path, gamma, from Y1 to Y2, you associate what? You associate holonomy Okay, you may say that we associate endomorphism. Not endomorphism. Now you associate a linear map, homomorphism, from Ly1 to Ly2. Now functoriality. Means that I call it F. That F, Y1, Y2, F, Y2, Y3, sorry, and here it's F, Y1, Y3. So it depends on gamma. Gamma 1, 2, gamma 2, 3. So that's what we do. First case, no geometrical enrichment. So in this case, it is nothing but connection in the vector bundle. However, you may consider also case where there is geometrical enrichment. There could be geometrical enrichment. In this case, formula would be a bit more complicated. So this is kind of a general story. Now let us see what you actually asked. You asked about what is time-dependent Hamiltonian. So time-dependent Hamiltonian is understood in the following way. I am just struggling in trying to write down you a proper picture. Here is the time that I call T capital. Here is our point. Here is again our point. Here is again our point. We will call it Y T1, Y T2, Y T3, etc. Then we have spaces V, oh, I call them L, LT1, LT2, LT3. Now you have intervals like this and like this, right? So what can you say? You can say that you have evolution F from moment T1 to moment T2, composition with F from moment T2 to moment T3 is f from moment t1 to moment t3. Right? So you could not. So there is no dependence on the time difference. You only can say is this. So you can solve it because this is holonomy equation. And you can save it saying that f of ti, tj is a p exponent of the integral from ti to tj of some h depending on t dt. And this is a theory of time-dependent Hamiltonian. Okay?
Okay, so it's still the same monoidal function.
You see, there is something that is hardly to change in this world. So it is hard to change the concept of being a functor. Okay? You may only change category a bit. Okay? So previously, objects were points, abstract points. And now they are points in time. And it fits with quantum mechanics. So what are you doing when you put electron in a magnetic field? You can turn this magnetic field on and off. Okay? And that's exactly what you will get. And this is this great answer for time-dependent Hamiltonian. So there were other questions. You see, I'm ready to answer.
There was question in chat at start of lecture, and I can't to understand it too. You said about classification theorem that all smooth cobordism like such as exponent. What is smooth cobordism in general case?
In general case, you mean in general dimension?
Yes.
Ah,
What is smooth for cobordism?
okay. So smooth cobordism means a smooth. So the most interesting equation in quantum field theory is how to construct this functors for dimension that is bigger than 1. And this is the most interesting equation, and I will answer it. I will speak about it after the break. Okay?
Excuse me, could I repeat question in Russian? I think you can understand. Я пытался спросить, там человек задал вопрос, что такое гладкость для кобардизма? Ну, как понять, кобардизм гладкий или нет?
Okay. Okay. So it's question to another semantic unit. So smooth cobordism is a cobordism given by a smooth manifold.
Ага, окей. Thank you.
And after the break, I'll speak about non-smooth cobordisms because they are also interesting. Okay?
Okay.
So now we definitely have a 12 minutes break. Let me continue. So, Maxim, is it possible to see me clearly?
Yes.
Okay, so just help me, because my camera is too sophisticated. And sometimes it decides where to focus. Now I'll try to answer the question about smooth cobordisms versus not smooth cobordisms. Suppose I have 2 points, A and B. And suppose I have 2 points, C and D. If I consider smooth cobordisms, I would say that they are just this one. It's what's called smooth cobordism 1. This is smooth cobordism 2. Okay. To avoid complication, it is a smooth cobordism 2. However, there is also non-smooth cobordism. So non-smooth cobordism so this is not a manifold. So actually, let me remind you that manifold is something, is a space that locally looks like a disk. So here it really locally looks like a disk. However, here this is not a disk. And if I make this thing smaller, it would never be a disk. So then you may ask, why do we care about non-smooth cobordisms? So you may say that, look, there are many pathologies in the world. Why should we care about this pathology? Okay? And there is a reason why. Non-relativistic.
There is very bad to see you because camera unfocused.
Okay, so please let me know. So camera decided to be unfocused. Thank you very much. Is it focused now?
50-50, but it's better than usually.
So here we have non-relativistic theory. When we have this process, and this is electromagnetic interaction, that is some enhancement of the cobordism. Still, we have two electrons incoming, two electrons outgoing. However, there is a relativistic theory. In relativistic theory, Feynman diagrams are examples of non-smooth cobordisms. Suppose you have electron, and suppose you have another electron. Here we have something like a bound state, and this bound state goes like this, and probably goes like this. Okay, so there is actually no bound state between two electrons. So let one be electron, another be a positron. Then they could annihilate to gamma quant. This gamma quant virtue could lead to, say, mu plus, mu minus, and they could annihilate again to produce E minus, E plus. So this is what people keep in mind in high energy physics. And people see these processes on accelerators. It's not the creation of mathematical brain. It's what really happens. So here we need non-smooth cobordism. Now we are coming to string theory. And actually, passage to string theory is to go from non-smooth cobordism back to smooth cobordism. But in one dimension higher. Okay, exclamation mark. So this is something non-smooth. This is not a piece of the manifold. This is not a piece of the manifold. How can we make it smooth? So instead of the particles, instead of the point, I will promote point to circle. This is smooth covariance. So how can I see this Feynman diagram in this string diagram? I want to make line thinner. Okay. So Maxim, do you see that this and this are actually the same?
Yes, this looks like each other.
And I can decompose it into cylinders, pans, and it will become smooth. Okay. So not smooth comes to smooth. And in this way, announcement. In this way, we get rid of ultraviolet divergence. But this is announcement. I am not explaining it at the moment. At the moment, I am discussing smooth cobordisms versus non-smooth cobordism. Okay. I am explaining something very deep. And that's why I want you to ask questions, because you cannot read it in books. You can read it in books what category is. But you cannot read in books what quantum field theory is. Or actually, what you will read in books would be completely outdated.
There is available way to calculate limit from string theory to field theory. Excuse me, let's say speak in Russian. Можно ли как-то перейти от теории струн к теории поля, вот сужая вот эти цилиндры в диаграмме?
Yes. How to go from string theory to field theory? Answer is like this. As you know, we associate to the circle the space L. Now,
Yes.
the space L would be infinite dimensional.
Mm-hmm.
We have a cylinder. We associate to a cylinder H, that is called Hamiltonian. on L. Now, it happens that H is positive demand, is positive, is semi-positive. So it has a spectrum. So let me draw the spectrum of H. It looks like this. And there is a gap here. And here is M string. And here is M string, etc.
Они там есть из-за того, что у нас цилиндр компактен, ну, в смысле,
Okay, so we will discuss it later. Yes.
Okay.
So the Hamiltonian here would be the spectrum of Laplacian of d over d sigma square on S1. And it is like k square. But this k square is multiplied by something that is called M string.
yes is clear.
So that's why you have this. That's why you have this structure. So this is low energy states. This is called field theory. Limit. And to go to this field theory limit, we need to forget about higher states, about these states. But we can get it taking cylinders long. So taking cylinders long is what physicists used to say. We would like to say that time times M string should be much bigger than 1.
There is length of cylinder.
Yes, T is the length of cylinder.
Uh-huh.
Okay.
Okay, thanks.
Okay, so today was a hard day for understanding. I do not want to hurry up. I do not want to jam. I would prefer to answer questions. So 5 minutes for questions, for asking questions.
But the Feynman diagrams in QFT. I mean the legs in Feynman diagram. The Feynman diagrams in QFT do not represent the trajectories of the particles, but in string theory, the tubes are the world sheets of the of the strings, right?
No, you are wrong. So when Feynman originally introduced Feynman diagrams, he actually thought of Feynman graphs as representing trajectories of the particle. It was his original idea. He actually was thinking about the quantum theory in classical terms, where you do have particles and where you do have trajectories.
So, but from the above scattering diagram of positron electron, the external legs have a specified momentum.
Yes.
So the wave package is everywhere. It doesn't have a specific location in space-time. So how can it be a trajectory of the electron position?
So
I thought the diagrams are in momentum space.
you are wrong. So first of all, Feynman was a physicist and not a mathematician, okay? So he was thinking about scattering as a point particle going from the far away. So for Feynman, it was like this. It's a particle going from far away along the straight line and interacting and then going far away again. So these were particles. For him, it were particles. So when you have particles and you understand it in terms of particles, then you may consider linear combination of particles. And when you and then you come to this issue of the wave packets. Because the wave packet is something that looks close to a particle. So he wanted to consider ingoing states, or psi, yes, ingoing, as e to them. I'll write it in for non-relativistic theory. So he wanted to consider the following wave functions that depend on p, x naught, and epsilon. So this is a wave packet. Okay. And you actually study what happens with wave packets. So we will, in our course, we will of course study wave packets. Later. In some detail. So this is kind of approximation. This is something like this, that travels with a speed that is p over m. And we need to put here t dependence. So we will discuss how to write it down. Okay? And of course, he was interested in scattering of wave packets. Then it turns out that technically, only technically, it is better to consider pure plane waves. But it was always scattering of particles for him. And the same happens with strings. Exactly the same thing. So either you are writing this, so here we have string propagation, or you are writing this, and here you put vertex operator. These two approaches are the same. And I'm even surprised to hear that you think that in string theory it is strings that propagate, while in field theory there is no particle propagating. There is a propagating particle.
But you said they are plane waves. Plane waves means they are everywhere in the space, right?
Okay, so plane waves is a linear combination. So plane wave is a linear combination of particle states. So let me go to Dirac notation. What is plane wave? Integral over dr. So it's how Dirac would write it. R e to the IPR. So plane wave is a linear combination of states of particles sitting at particular points. And quantum mechanics, of course, is about linear combination. Let me give you one more argument. In quantum field theory, you know that you're writing a Green's function between R1 and R2. And one of the ways to write this Green function is to say that it is a e to the p mu square, that it is 1 over p mu square. And then you take integral kernel. Okay? So 1 over the Lambertian. Now, it's interesting to note that this thing is 1 over p squared in momentum representation. However, this is the following. And this is called Schwinger. representation. So let me continue. This is an integral from 0 to infinity, dt. Now, what is e to the minus t D'Alembert? It is the integral over trajectory and here we have this action x mu dot square d tau. So what we see here, that in order to get this thing, we should consider particles. In space-time. And then we should integrate over trajectories of these particles. So this t is called proper or Schwinger time. So here we have these particles. And when we integrate over the Schwinger time, you get exactly the propagation. So whenever you have 1 over the Lambertian, you have these particles. Okay? Bitcoiner.
Yes, I've seen this Schwinger formulas. But I never thought the x mu represent any physical particle.
So there are two things in the world. There are formulas and there is interpretation. Okay? So these are correct formulas. And now let me give Feynman interpretation. So Feynman interpretation says that here we have trajectories, these trajectories, and we are integrating over this wavy trajectory. And if you have propagator here, I don't know. Let us consider the simplest diagram. Feynman says that we are integrating over such trajectories. So here trajectory is a straight line and here it's wavy. Okay? Now let us consider more complicated process. Like this. So we replace each propagator by wavy trajectory, these trajectories. So altogether, you are integrating over the trajectories. And these trajectories form a graph. And this was original Feynman's idea that mathematics, and this is mathematics of field theory, may be replaced by physics of trajectories in the space-time. And after, yes?
Is the parameter t a kind of one-dimensional analog of tau in upper half plane in string theory?
Yes, of course. But things are reversed. So this parameter t was introduced by great Julian Schwinger in 50s. who said that what we are doing is the following. We have graphs. Not topological graphs, but metric graphs. So graphs with metric associated to intervals. And then if we want to integrate, if we want to get an amplitude, we just need to integrate over these t's. And then later on, it was Siegel, not Graham Siegel, but another Siegel, Warren Siegel, and Polyakov, who interpreted these t's as one-dimensional gravity. So Polyakov interpreted it as a one-dimensional gravity to say that in string theory we have two-dimensional gravity. So of course, it is like this. It's what you should start with if you are studying quantum field theory. But everything depends on the books that you are reading. So formulas are the same. The important thing is what is behind the formula, what people say orally or type in text. Interpretation is very important because understanding comes in interpretation of the formula. Okay? So today, so it's enough for today, I think. My new rule is that I would not make you tired. Otherwise, you would not attend my lectures.
Excuse me, I have a question. Sorry.
Yes.
As I don't know physics knowledge much, I have an elementary question. At the beginning of the class, you used the linear space function over R3 tensor C2 to denote the phase space. But I wonder, why don't we use R3 tensor C2 directly? Why do we use the function space, the function over R3? Is there any physics explanation?
Yes. So
okay.
So yes, of course. So when we think about particle, okay, when we think about particle, we should assume that particle is something that could sit at different points in our space. Okay.
Okay.
So there should be an operator such that its eigenvalues would be positions of the particle. It's an axiom of quantum mechanics that I'll explain next time. But since you have a question right now, I'm explaining it right now. So you should have a space where you have infinitely many eigenvalues. And this space has to be infinite dimensional. So so probably you are a mathematician, and that's why I can explain it to you in terms of the spectra of the commutative algebra. Okay? If you would like to describe points on the complex plane, you need infinite dimensional algebra of polynomial. Okay?
Yeah.
So this space of states is like, not exactly. is like this space of
polynomial
polynomials.
ring. Yeah, yeah.
However, if you have a spin degree of freedom, you probably heard that spin could be up and could be down. It can
Yeah.
have only two values. So that's why the space of states C square is enough.
Okay.
But we will discuss all this in detail during the course.
Oh, I see. All the state is seen to be something like prime ideals in the polynomial ring.
Yes, but
Like
not prime, maximal ideals.
Yeah. Including the spin state is seen like functions in just in C2, not
Okay,
a two state. Okay.
So we will discuss it in some detail.
Okay.
So what are states? What are observables? How do we see particles? We will discuss it in some detail.
Okay, thank you. I have very little knowledge in quantum physics.
You see, you do not need to have. So we will discuss it. I told
Okay, thank you.
this to let people know that what we are doing is not something very abstract. You see?
Yes.
So people are coming to course on quantum field theory. And then what do they hear? Cobordisms, functors, okay?
Okay.
They have a question why this is related to physics. So I will do the following. Sometimes I will talk in pure mathematical language, and sometimes I'll talk on the language of mathematical physics. So in the language of mathematical physics, you are including important remarks explaining how constructions are related to what people used to see in physics. So in physics, people study scattering processes, bound states, and many other things. So my question was how this is related to cobordism. So mathematicians invented cobordisms for another reason. They wanted to study topology of smooth manifolds. But this construction turned out to be very important. And it is much more, and it turns out to be very important when we consider enriched cobordism, geometrically enriched cobordism. So people in pure mathematics are never doing this geometrically enriched cobordisms. What for? Okay? However, it is exactly this construction that is important for quantum physics. Any other questions?
No, thank you.
Okay,